Hi, this is Professor Pradyot from Leadib Academy. So we are discussing IBDP Chemistry HL Paper 2 of May 2019. And I have already indicated the paper reference number, okay? So what is interesting is that we are not just providing the video solution, but I'll be explaining the underlying concepts for your deeper understanding, okay? So you will find it very, very interesting, okay? And we at Leadib Academy also provide the courses for all the important subjects of IBDP like chemistry, physics, maths, and which we are basically uploaded on our website. So please do visit our website, leadibacademy.com. Okay, and you can subscribe to those courses. Okay, let's begin with question number 5A1. A carbonated water is produced when carbon dioxide is dissolved in water under pressure. So they are giving these equations, okay? This is the first, CO2 gaseous under the water, becoming aqueous, CO2, okay, CO2 aqueous. Then CO2 aqueous will further react with H2O, water, and it will produce H plus and HCO3 minus. So question is being asked, carbon dioxide acts as a weak acid. Distinguish between a weak and a strong acid. So first of all, what example is this? CO2 gas, okay? CO2 gas is being bottled under, okay, under pressure. So CO2 gas, okay, is being under pressure, okay, it is being put in. So which reference you can think of? Straightforward carbonated drinks, okay, like Pepsi, Coke, etc. So what happens under the pressure? Okay, the CO2 gas will dissolve, okay, it will dissolve in water. Anyway, this is for your reference. This is as per the Henry's law. Okay, that is not part of the discussion, but as per the Henry's law, the higher the pressure, more amount of CO2 can be dissolved. Anyway, so this is what is the equation, that CO2 in aqueous form, that means CO2 gas now has been dissolved in water. Now CO2 has come in this. This is in the aqueous form. Now what happens, that CO2 aqueous will further react with this water, because this is the water which is there. It will start getting, and it will start forming H plus ions and hydrogen carbonate or bicarbonate ions. Okay. So CO2 and H2O, basically this is nothing but our carbonic acid, H2CO3. Okay, let me write it properly. Okay, use some different colors, so there's no color. So this part is nothing but a carbonic acid. Okay, that is H2CO3. And that basically can dissociate into H plus and this. Okay, now the question is being asked, okay, it acts like a weak acid. What does it mean? Simple. The difference between strong and weak acid, okay, is like this: strong and weak. What is the key difference? In strong acid, almost complete dissociation, and in weak acid it is partial dissociation. So let's understand what is mean by this. Simple logic, that in case of this, okay, CO2 plus H2O, which is nothing but a carbonic acid, okay, it is not going to get completely dissociated, okay, and that is indicated by these reverse arrows. Okay, that means the reaction is going forward as well as reverse, backward. Okay, so that's the reason, and therefore this is the partial dissociation. That means it has not been completely dissociated, 100% dissociation. For example, if you would have taken HCl, okay, it would have got completely dissociated. What does it mean? That means there is a single headed arrow, okay, only in the forward direction. There is no this one, okay, there is no reverse reaction, only one directional kind of a reaction. While if it is a partial, that means it's a reversible reaction. That means it is not 100% dissociated, it's just a partial dissociation. So in case of weak acids, there is a partial dissociation, and in case of strong acid, there is almost 100% dissociation. Okay, that's the key difference. And carbonic acid or carbon dioxide is acting like a weak acid. Okay, and that is being shown like this. Okay, double headed arrow, one going forward, this is for the forward, and this is for the backward. Okay, extremely simple concept, but very important concept. Okay, let's look into the question number 5A2. The hydrogen carbonate ion produced in the equilibrium 2 can also act as an acid. State the formula of its conjugate base. Okay, so they are referring to this reaction, equilibrium 2. So what is getting formed? CO2 aqueous plus H2O. I'm not writing the phase or states. H plus and hydrogen carbonate. So what is being told that even hydrogen carbonate, this is the hydrogen carbonate, this can act like an acid. So what does it mean? HCO3 minus, okay, can get decomposed, okay, not decomposed, dissociated into H plus and CO3 2 minus. Okay, or ideally I should be saying, okay, let me rewrite this so that it is a better one. HCO3 minus plus H2O, and this I'll write as H3O plus. Okay, to make it very clear. So in this case, please remember that this is acting like an acid. Why? Simple, because as per the Bronsted and Lowry, okay, the one which donates proton, so it had donated proton. So if we take out the proton minus H plus, that means we are taking it out, what we will get is its conjugate base. This is its conjugate base, CO3 2 minus. So acid, why acid? Because it had donated proton. It has given away, gifted to this H2O, and that's why H3O plus is getting formed. In short, H2O plus H plus from HCO3 minus has resulted into H3O plus, hydronium ion. Okay, so it means this acid bicarbonate ion has gifted one proton and it has become CO3 2 minus, that is a conjugate base. And obviously this is, water is acting like a base, and this is conjugate acid. H3O plus is a conjugate acid. Very, very straightforward. Okay, hope this is quite clear and very interesting. Okay, let's look into the question number 5B. When a bottle of a carbonated water is opened, these equilibria are disturbed. State giving a reason how a decrease in pressure affects the position of equilibrium one. Okay, so first of all, let's understand what is the situation. So this is the bottle, okay, and this is the cap. Okay, and this is that whatever carbonated water or carbonated drink, and it is under pressure. Okay. Now, when we open this bottle, okay, this cap is open. So what is happening? Okay, the pressure at the top is going to get reduced. Okay, the pressure on the top is getting reduced when we open the cap. Okay, the cap is open. So pressure is getting reduced because whatever that CO2 gas was there, okay, so the pressure is going to get reduced. Now what is happening? Let's look into this equilibrium. CO2 gas is in equilibrium with CO2 aqueous. Okay, now please understand that in case of this, okay, now the interesting point is that in the forward direction there is a decrease in the forward direction there is a decrease in number of gaseous moles because it is getting converted into liquid. Okay, the CO2 gas is getting dissolved. That means the moles of CO2 or particles of CO2 which are remaining in the gaseous state are decreasing, okay, in the forward direction. So, and in the backward direction it is increasing. Okay, that means CO2 aqueous is getting converted into CO2 gas. Now, as per the Le Chatelier principle, we have seen that as per the Le Chatelier principle, okay, if there is a decrease in the pressure, okay, the backward reaction will be favorable. Backward reaction, okay, because there is an increase in moles. Decrease in pressure, okay, will to ensure that there is a proper equilibria, okay, to maintain the equilibria, the backward reaction will be favorable, okay, as per the Le Chatelier principle. Simple. It means backward reaction means that from the CO2 aqueous, okay, the CO2 gas will start coming out. That is what we call a fizz. Okay, it will start coming out. So the CO2 gas will start coming out. Okay, this is how the carbonated drinks or carbonated water work. Okay, this is a simple principle. As soon as we open the cap, the pressure on the top gets reduced, and because of that, the solubility of the CO2 gas, which in the water, will get reduced, and CO2 gas will start coming out. Simple logic. Okay, this is how it works. Hope this is quite clear. Very, very simple. Okay, so question number 5C. At 298 Kelvin, the concentration of aqueous carbon dioxide in carbonated water is 0.20 moles per dm cube, and the pKa of equilibrium 2 is 6.36. Calculate the pH. So the thing is basically it is being referred to this equation, okay, equilibrium 2. This is the equilibrium 2. So CO2 plus H2O giving us H plus and HCO3 minus aqueous. Okay. So what information is available to us? So let's understand, we have been given pKa. Okay. What is P? P, if you recollect, okay, P means nothing but minus log of 10. Whatever you put it, it will become P. Okay. So P corresponds to minus of log of to the base 10 of anything. So in this case, it corresponds to minus, okay, log of 10 to K. Simple. Okay. So this is given as 6.36. So let me remove this. Okay. So now with this simple logic, we can say Ka is equal to 10 raised to minus 6.36. Simple use of logarithms. And that will give us, by putting in the GDC, we will get 4.37 into 10 raised to minus 7. What is K? K is the dissociation constant of this acid. Okay, because CO2 is acting like an acid. We have already seen that. Okay, even though it's a weak acid, and that is also getting confirmed because Ka dissociation constant is very, very small, 4.37 into 10 raised to minus 7. That means very, very, very small quantity. Okay, so it confirms that it is a weak acid. Okay, now what we need to calculate? Okay, because finally we need to calculate the pH. That means somehow we have to calculate H plus. Okay, proton concentration. So let's use our formula. Ka is equal to, we are referring to this reaction, okay, or this equilibrium. So what will be Ka? K will be H plus multiply by HCO3 minus divided by CO2. Okay, and this is obviously all aqueous, aqueous, aqueous. Now since H plus, okay, is equal to HCO3 minus concentration, so we can write this as H plus square divided by CO2 aqueous. This is also aqueous. Why? Because the reason being that the concentration of proton H plus can be assumed, okay, can be assumed to be equal. Okay, now let's try to use this information. And how much is the K? K we have already calculated. Okay, so let's write it down. K is equal to this. Now let's start substituting. K is 4.37 into 10 raised to minus 7. H plus square we need to calculate. And how much is the CO2 concentration? It is already given. The concentration, okay, of aqueous carbon dioxide in this is 0.2. So that means this is 0.2. Do the calculation now and calculate H plus. Okay, simple now, just cross multiplication. This will imply concentration of H plus will be, okay, by doing the calculation, you can do it yourself. I have already done it. 2.95 into 10 raised to minus 4 moles dm cube. Okay, this is H plus. And now the last step, formality. how to calculate the pH. Let me use a different color to calculate pH. So pH is nothing but minus log, okay, to the H plus concentration, that is minus log to 2.95 into 10 raised to minus 4. Again, use the JDC and you should be getting 3.53, the pH. What does it indicate? It is definitely acidic. There is no question on that. But important that it is not very, very low. That means this indicates that it is a weak acid. Okay, CO2. Okay, it is a weak acid, because if it would have been strong acid, you would have got around 1.2, 1.3, something like that. Okay, 3.5 to 4.5, that means it's a weak acid. Okay, so it was a very, very simple calculation, formula based. Just apply the concepts. Okay, the only concept what you are supposed to is to use this K formula. K, dissociation constant, is H plus into HCO3 minus divided by CO2. Okay, extremely simple logic. Okay, a little bit calculations involved, but it is quite easy. Okay, hope this is quite clear. Let's look into the question number 5D1. Soda water has sodium hydrogen carbonate. Also, it is called as sodium bicarbonate, NaHCO3, dissolved in the carbonated water. Identify the type of bonding in sodium hydrogen carbonate. So first they are asking between sodium and hydrogen carbonate. Okay, so let's try and understand. This is NaHCO3. Now please note this, that sodium is the alkali metal. So alkali metal means we know that they form ionic bond. Okay, that is the characteristics of alkali metals. So it will be between, okay, and alkali metal, they are electropositive. So what kind of a bond we can expect? Ionic bond, simple. So it is going to form Na plus and HCO3 minus. So this is what we called, okay, let me, sorry. Oops, sorry. Okay. So this is ionic bond or electrovalent bond. Why? Because sodium alkali metal, okay, group 1, so it is having a tendency to lose one electron and form like Na plus, and that will be accepted by HCO3 minus, and it is forming, okay, basically a ionic bond. Okay, so there's a transfer of electrons and it is an extremely strong bond. So alkali metals, they typically form ionic bonds. Now the second part, that between hydrogen and oxygen in the hydrogen carbonate. So let's draw this structure. Carbonate. Let me use this. We know this. Oxygen. Okay. O. And then there is H. Okay. Now the question is being asked. Okay. So why I'm showing like dotted? Please remember, This is resonance, okay, resonating structure. Okay, it's a very, very clear cut, this one, that, okay, this is the resonating structure. Therefore, the bond between carbon and oxygen is neither single nor double. Okay, we can think like it is like a 1.5 bond. But a question is being asked between hydrogen and oxygen. So the question, so simple, in case of whenever hydrogen is attached to oxygen, we are very, very well aware of that it will basically lose, okay, the electron cloud. Oxygen is more electronegative, so hydrogen will start losing its electron cloud and it will acquire a partial positive charge. Oxygen will acquire partial negative charge, and we will get basically this bond will be, okay, a polar covalent bond. It is not only covalent, not ordinarily, but this is the polar one. Okay, it is like a polar, this one, because of the electron cloud shifting. Okay. As a matter of fact, now this hydrogen will be capable of forming the hydrogen bonding with the other molecule. Okay, so that is the logic. But in case of this question, so there are two kinds of bonds: NaHCO3 sodium, Na plus, and HCO3 minus ionic bond, and between oxygen and hydrogen, okay, it is basically polar covalent bond. So it is a covalent and this is ionic. Okay, that's the difference. Hope this is quite clear. Interesting. Okay. Interesting question 5D2. Predict, referring to equilibrium 2, how the added sodium hydrogen carbonate affects the pH. Assume pressure and temperature remain constant. So let's write it down. The equation: CO2 aqueous plus H2O liquid, okay, H plus and HCO3 minus, and then NaHCO3, okay, aqueous, it will get dissociated. Being a salt, it will be always in this. Okay, okay, now let's see what is the interesting phenomena. Okay, this is called, now let's understand that whenever NaHCO3 is added to this, please remember that this is the weak acid. Okay, so whatever is the dissociation, this is the weak acid. So because of that, there are very few bi-hydrogen carbonate ions are there initially. Okay, because of the CO2 being a weak acid, because we know that it's a partial dissociation. So there will be very few hydrogen carbonate ions. But NaHCO3, it is being a salt, it always dissociates almost completely. So this hydrogen carbonate ion coming from NaHCO3 is going to be very high. Okay, so what is the effect? So overall effect is that hydrogen carbonate ion concentration in the solution is going to increase. Okay, hydrogen carbonate ion concentration is going to increase in the solution after adding NaHCO3. So what will be the effect? According to the Le Chatelier principle, okay, if we increase the concentration of HCO3 minus, the reaction will shift backward. Okay, reaction will start shifting backward. Okay, I wrongly shown, sorry for my mistake. Even Okay, I should be showing only with the single headed arrow. Sorry for that, because it's a complete dissociation. Okay, just note this. Okay, sorry. Okay, so it is going to go in the backward direction. Okay, the reversible reaction, it will start moving into the backward reaction. So what is mean by that? That means H plus proton will start reacting with hydrogen carbonate ion, and it will start forming back CO2 and H2O. Okay, so what is the effect? The effect is that H plus ion concentration will start decreasing. Okay, H plus ion concentration will start decreasing. H plus ions concentration in solution will decrease, and we know that if H plus ion concentration decreases, the pH will increase. Very simple. Okay, and by the way, when we add these two ions are common, so we call this as common ion effect. Okay, this is basically nothing but common ion effect. That means we add one of the common ions. Because of this, the dissociation of the weak component, whether it is a weak acid or weak base, suppresses. It gets reduced. That is what exactly we are using the concept. By increasing the concentration of hydrogen carbonate ion, okay, the dissociation of CO2 aqueous decreases. So what is the effect? Because of that, H plus ion concentration will decrease. If there is a decrease in the H plus ion concentration, the pH will increase. Okay, this is the net effect. Hope this is quite clear and very interesting kind of a question. Okay, based on Le Chatelier or common ion effect. Okay, extremely simple. Okay, 5D3. 100 centimeter cube of soda water contains 3 into 10 raised to minus 2 gram of NaHCO3. Calculate the concentration of NaHCO3 in mole per dm cube. In short, you are aware of, we call this as molarity. Okay, this is how we express molarity, concentration. So what is the formula? Simple. Molarity is equal to number of moles of solute, in this case NaHCO3, divided by volume of solution in dm cube. That's all. Okay, so let's start converting it everything. Okay, first we will check. Okay, it is given as 100 centimeter cube. So first we converted our volume, keep it ready. Volume of solution is 100 centimeter cube. So convert it into dm cube. Okay, so that is 10 raised to minus 1 dm cube. So volume we are ready. Now let's calculate the moles. So first we will calculate molar mass of NaHCO3. So it would be 1 into 22.99. From where we are getting this? It is from the data booklet. Okay, 22.99 is the atomic mass of sodium. Then comes the hydrogen, that is 1 multiplied by 1.01. Okay, H. Then C, it is 12.01. So 1 multiplied by 12.01. Sorry, let me be very clear. Okay, and plus 3 into 16. This is for oxygen. So how much will be the molar mass? It works out to be 84.01 gram per mole. Okay, this is the molar mass. Now how to calculate moles? So moles of NaHCO3 will be, okay, 3 into 10 raised to minus 2, okay, 3 into 10 raised to minus 2 divided by 84.01. Okay, these are the moles. Okay, these are the moles of NaHCO3. So let's calculate the concentration, okay, of NaHCO3. Now it should be straightforward. Take the moles, that is 3 into 10 raised to minus 2 divided by 84.01. These are the moles divided by, so these are the moles, and the volume of the solution is 10 raised to minus 1 dm cube. Quickly do the calculations and you should be getting 3.6 into 10 raised to minus 3 mole per dm cube. Okay, quite simple. You should be aware of how to calculate molarity, very, very important way, okay, method of expressing the concentration. And if you are interested in understanding in more detail, okay, please subscribe to our courses, because we at Leadib Academy, we have prepared the courses for chemistry, physics, math. So you can very well subscribe to our courses by visiting our website, okay, www.leadibacademy.com. Okay, very simple.